specifically it's called a geminal diol. Why do you think it's called a geminal diol? What does geminal mean? No astrologers here?
Gemini.
Twin. From the Latin word for twin. Geminal diols have twin alcohol groups because they're attached to the same carbon. There is another type of diol where the two OH groups are not on the same carbon. That's also a diol, but it's called a vis diol. That vis is short for vicinal. Nobody takes Latin anymore, but vicinal means neighboring in Latin. So you have your neighboring diol and your geminal diol. In fact, that vicinal diol right there is a very important one. That's ethylene glycol. If you drove your car today, that's what kept your radiator from overheating. About a 50% solution of ethylene glycol in water raises the boiling point, lowers the melting point, makes a nice coolant. Okay, but getting back to this gem diol, which is the hydrate of this aldehyde, since this is also an alcohol, if you target these two hydrogens to be lost, OH, CH, which is how we produce the carbonyl in the middle in the first place by removing OH and CH. You remove those two hydrogens, one from one of the OHs and then the CH, you get something you've seen before, that's acetic acid. So through the diol, the oxidation product in the middle oxidizes a second stage even further to a carboxylic acid. Aldehydes do this uniquely. In fact, aldehydes are the most easily oxidized class of organic compounds. Even in air, aldehydes oxidize. Their air itself contains enough oxygen to oxidize aldehydes. And of course, this is why a cheap bottle of wine has to be drunk very fast, because it goes bad, it goes acidic, produces acetic acid. When you make wine, you ferment it, bacteria produce ethanol, and then produce enough ethanol so that it suppresses the activity of the bacteria, and the wine becomes stable. That's around 11 or 12% alcohol. If you buy a cheap bottle of wine, it will often say 10%. That's a disaster because the fermentation process is still going on, and once you pop the cork and add air to that mix, then you start producing acetic acid, which, like any acid, well, vinegar is 2% acetic acid, so the wine develops this vinegar taste to a very sour taste. It's a very natural thing. And also, dairy products, butter, for instance, contains this aldehyde right here. Very well-known four-carbon aldehyde that for hundreds of years has been known as butyraldehyde. In fact, that's where the word butter comes from. Butyraldehyde, like most aldehydes, has a very, very subtle and pleasant odor and taste. Aldehydes are what's in very, very expensive perfumes. Aldehydes are the most expensive class of organic compounds because you can't store them easily. They oxidize on you. But butyraldehyde is what gives butter that unique taste that everybody can't resist. And of course, dairy products contain lots of butyraldehyde, and part of what you get from rancid dairy product is butyric acid, which is the oxidation product. From butyraldehyde, you get butyric acid, which makes the milk that's been in the refrigerator too long taste sour, and dairy products start to get kind of a nasty odor. It's oxidation. And aldehydes are very, very common natural products in all dairy products. And lots of flours use aldehydes to attract insects to them, bees, etc. So these are very important compounds. Again, don't worry about the reagent, just know what it does. It has to remove two hydrogens. And don't be fooled by this reaction here, because it's really the hydrate that's oxidizing. So if there's water present, the aldehyde is at least partially in the hydrate form, the diol form, and as that oxidizes, you know how an equilibrium works. If you remove one of the products, the equilibrium shifts to replace it. So it's like a pinhole in a balloon. As the diol oxidizes, it drains your aldehyde concentration until all of it is oxidized. And again, reduction is the opposite. You just have to find a reagent that will put those two hydrogens back, if you will, on the carbonyl. One on the carbon, one on the oxygen. So when you look at that chapter, you'll see some very exotic looking reactions, but that's all the reagents do. And this is always done in two steps. So these two hydrogens, by all of these water-based or ionic oxidations and reductions, it always adds one hydrogen and then the other, or removes one hydrogen and then the other. There are some free radical additions of hydrogen that can add both hydrogens simultaneously, but not with carbonyl compounds. We'll see that with alkenes and alkynes. And I should point this out right away. The two types of double bonds that you see all the time are carbon-carbon and carbon-oxygen. Consider them as two very different species, primarily because the C double bond O is polarized. The C double bond C is not. This is nonpolar. This is polar. So the types of reducing agents, for instance, that work with carbonyls don't work with carbon-carbon double bonds. And vice versa. The ones that work with carbon-carbon double bonds don't work with carbonyls. Because remember, everything's electronic. So to molecules, a carbonyl looks very, very different from an alkene. Okay, so let's see. 8.3, section 8.3 was on acidity of alcohol. That's all about removing that OH hydrogen. Now, you need a base to do that. So if you have an alcohol, you need a base to remove that proton. KOH is not a good base for this because it produces water which is pretty much the same acidity as the alcohol. So you're kind of fighting that lack of acidity and that competition. You're going to produce an equilibrium that's not going to work right. You need a stronger base than hydroxide ion. This takes you into a collection of bases that you'll start seeing that are what I like to call waterless bases, no water. Water is a really dramatic environment. If you have water in your system and you add any base to it, the strongest base you can generate is the hydroxide ion. It's called the leveling effect of water. So if you put a base in that's 10 times stronger than the hydroxide ion, the water will just react with it and produce the hydroxide ion. And it's called the leveling effect of water. So if you need a base stronger than the hydroxide ion, you have to get rid of the water. You have to go non-aqueous. And a common one is sodium hydride. NaH. It's actually Na plus H minus. It's really a salt. Now it looks really odd until you work with it and you realize that that's your problem and the sodium hydride doesn't have any problem existing at all. In fact, I have big jars of it in the lab. It's a salt. It looks like table salt. You can't get it near water. If you get water next to sodium hydride, the base part of sodium hydride you want to think of as H minus. Now you don't see, you probably haven't, maybe never seen H minus before, but it's actually more common than H plus. You can't see H plus in a bottle, but you can see H minus. The sodium, you can buy sodium hydride, potassium hydride, lithium hydride. They're very, very reactive with water, but you just keep them dry. So H minus will pull a proton off the water and produce hydrogen gas. So H minus plus H plus gives H2 and leaves you with sodium hydroxide. Again, that's the leveling effect of water. But if I keep water out of here and just add the alcohol, then the alcohol will give up the proton to the sodium hydride and produce the sodium salt of the alcohol plus hydrogen gas, which I can get rid of easily. And so I can produce 100% of the sodium salt of the alcohol. And that's the way you would typically do it. Now there is an alternative that you've actually seen before. If you take an OH, let's say water, and you drop sodium metal into it, what happens? Somewhere you've all seen somebody drop sodium into water. It blows up. The sodium metal undergoes a redox reaction with the water, and you get hydrogen gas being generated plus sodium hydroxide, and it gets so hot that it eventually ignites the hydrogen gas and pops or explodes. So you can just drop sodium metal and start producing sodium hydroxide and hydrogen gas. Now you can do exactly the same thing with an alcohol. That will produce the sodium salt of the alcohol plus hydrogen gas. ROH or HOH, what's the difference? works just as well. And a lot of times that's how we make the sodium salts of alcohol in the lab. What you can also do is just buy the salts of the alcohol. I have big bottles of sodium ethoxide also up in the lab. Looks just like salt. It's perfectly stable white solid, not a big deal. Just like having a bottle of sodium hydroxide, you can have a bottle of sodium methoxide, a sodium ethoxide, potassium T-butoxide is very common, potassium salt of T-butyl alcohol. Okay. And we'll see more of these, what we call non-aqueous, very strong bases. They're typically what you use for removing very difficult hydrogens that have very low acidity. Okay, now there is some base character here also. So the OH is truly a versatile functional group. It's not only acidic, but it's also basic because of the non-bonding electrons on the oxygen. Now don't get carried away with that. It's a very weak Lewis base. So let's say you add some sulfuric acid to an alcohol. That will start to protonate the alcohol, but it's in equilibrium. Now, sulfuric acid is a very strong acid, so if you add a lot of sulfuric acid, you would produce a lot of protonated alcohol. But that's just a Lewis acid-based reaction, proton reacting with the oxygen. And it's always reversible. Anytime you see an alcohol that looks like this, feel free to remove the proton so that you can look at just the plain neutral alcohol. Because OH is never permanently protonated. I could throw in potassium carbonate, for instance, and neutralize all of the acid and just have the neutral alcohol. So the protonated alcohol is to be viewed as just a temporary derivative of the same alcohol. But it does change the chemistry of the alcohol dramatically. In particular, you've learned in the chapter on alkyl halides about leaving groups and nucleophilic substitution. That's the whole deal with the SN2 and the SN1 substitution. The halogen's a good leaving group. OH is a really bad leaving group. It virtually will never leave because the carbon-oxygen bond is extremely stable. Next to carbon-hydrogen, carbon-oxygen is the next most stable bond. That's why we have so many oxygenated organic compounds around. So that OH is a very poor leaving group. But once you protonate an OH, it's an excellent leaving group.
Transition state complex.
So, for instance, if you were to think about an alcohol, just a generic alcohol, for some reason losing the leaving group, the OH, that would produce a carbocation, which is, of course, a nasty, unstable species, plus another unstable species, a hydroxide ion. If you protonate the alcohol, you produce the same nasty carbocation, but instead of a hydroxide ion, the leaving group is one of the most stable molecules on the planet, H2O. So there's a huge thermodynamic advantage to the bottom reaction over the top one. So a protonated OH becomes a very loose group. It's very likely to get bumped off. So that changes the chemistry dramatically. Protonated, and going back to this idea of biological chemistry, alcohols are everywhere and very stable, but if you protonate the OH, that is like flicking on a light switch chemically. That now is extremely reactive because the protonated OH is poised to leave. So that opens the door to all kinds of substitution and elimination reactions biologically. A protonated OH is even better than a bromine as a leaving group. Now, of course, your body doesn't like chlorine or bromine, so it doesn't want any of those around. But to make good leaving groups for nucleophilic substitution, which is the most common biological reaction, all it has to do is protonate an OH. And it has many proteases that do just that. These are enzymes that can deliver a proton,
Next 10 months,
just like FedEx delivers a package to your house. You know, in the lab, when we add sulfuric acid to deliver protons, it's like dropping 1,000 packages out of a plane and hoping one of them hits your house. The protease does exactly the same thing, delivers the package, but takes one package, goes right for your house, and drops it off. So this enzyme is able to recognize this molecule, knows where the oxygen is, coordinates with the molecule. Now, not magically, it does it by space fitting and hydrogen bonding and dipole-dipole attractions. These are all codes that can allow an enzyme to say, that's ethyl alcohol, and I know where the oxygen is, I coordinate with it, and then all the protease does, and it may have a molecular weight of 600,000, all it is a delivery device for a proton. Just drops it where it's supposed to be. The OH gets protonated, the reaction goes like a shot. Now, when you want to shut down that reaction, and this is important in biological chemistry, your body needs to be able to start a reaction immediately and then stop it immediately. All you need to do is remove the protease. And no more protonated OH, no more nucleophilic substitution. So what an organism needs chemically for organic reactions is the equivalent of a start-stop button or a light switch. Start the reaction, stop the reaction. And of course, a lot of biological malfunction has to do with reactions that don't start when they're supposed to or don't stop when they're supposed to. So that's what this is all about in terms of the acidity. We'll see some examples of this as we get into 9 and also the chapter on alkenes. Okay, so acidity of basicity. And in freshman chem, you learned that that type of molecule that can be both an acid and a base is called amphoteric. Just a fancy word for dual behavior.
Maybe
So
even the book,
we're
I don't know.
skipping a couple of sections, and then it gets to the section on oxidation and reduction involving alcohols. Oxidation of alcohols to aldehydes and ketones, reduction of aldehydes and ketones to alcohols. You still need to know that reaction, but strip away all of the specific reagents. You just put bracket O for oxidation, bracket H for reduction, and know how to take off the two hydrogens and add the right two hydrogens in the two different processing. So that reduces that to something very simple. We'll get back to the details later, because when we get to aldehydes and ketones, we'll have to revisit this.